Assalamualaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. In the last part, we have looked at the pressure variation with elevations. Generally, any surfaces which are in touch with fluid will be subjected to pressure. And because pressure is force divided by area, the surface will also be subjected to hydrostatic force. And we have to make sure that the equipment or the structure is strong enough to resist this hydrostatic force. For example, if we have a dam, so the dam structure has to be designed such that it is strong enough to withstand the huge hydrostatic force due to large amount of water that it contains. So if we consider, for example, a dam, let's say this is the dam, and this is the water level. So there will be hydrostatic force due to the pressure. And if we plot the pressure variations with Z, we will obtain the distributions like that. So at this point 1 here, whereby the height there is h, the pressure will be equal to rho g h1. Whereas at this point here, 2, the pressure, let's say this is h2, this is h1, the pressure will be equal to rho g h2. So the pressure varies linearly, so hence the force acting on the surfaces at different points on the surface of the dam will be different. So we need to determine the total hydrostatic force acting on the dam surface, as well as the line of actions of the net hydrostatic force acting on the dam surface. A surface submerged in a liquid can either be a curved surface or a flat surface. Let us first of all consider the hydrostatic force on a submerged plane surface. Let's say this is the surface which is submerged in a liquid. So if you view from the edge, all you can see is just a straight line like this. Since the surface is in equilibrium, the hydrostatic force acting on this side and on this side are the same. But in our analysis, we would like to determine the hydrostatic force acting on one side of the surface only. So let's say the surface here is slanted at an angle theta with the water surface. Later, we will show that the total hydrostatic force acting on the surface will be equal to pressure at the centroid of the surface multiplied by the area. So let's consider a plane surface submerged in a liquid. So let's say this is the plane surface. And let's say this is the H view of the surface. So it's slanted at an angle theta. And let's see if you view from normal to the surface, you will get surface, let's say, looks like this. And let's define our origin at the centroid of the surface. So this is the centroid, and that is our x directions, and y direction is in the directions parallel to the H view of the surface. And then I'm going to define the vertical distance of the centroid from the water surface as h bar, and the slanted distance of the centroid to the water surface is equal to y bar. So we can see that h bar is equal to y bar sine theta. So this is the edge view of the surface, and this is the normal view of the surface, and the area of the surface is equal to A. Let's consider a small area here. So the equivalent area from the edge view is there, and the area there, the area is dA, and the height of that area from the water surface is equal to h. The hydrostatic force acting on this small area, let's call that dF hydrostatic. Now let's consider hydrostatic force acting on dA, which is equal to dF hydrostatic. So dF hydrostatic will be equal to the pressure there multiplied by dA. But the pressure here is equal to rho GH. So rho GH dA. But if we consider H is equal to H bar plus this distance here. This distance from the centroid to A is y. So the vertical distance equal to y sine theta. So if we substitute this to here, so we'll get the expression for the F hydrostatic, which is equal to rho g h bar plus y sine theta dA. Now, in order to get the total force acting on the surface, we will have to integrate over the whole of the surface. So the total hydrostatic force acting on the surface, F hydrostatic, will be equal to integrations of dFH, so integrations of rho g h bar plus y sine theta dA over the whole surface. So if we expand this, so we have rho g is just a constant, h bar dA plus rho g sine theta y dA. So this is just equal to rho g h bar A plus rho g sine theta y dA. By definitions, since the origin is at the centroid, the integrations of y dA is equal to 0. So this is 0. So we have F hydrostatic is equal to rho g h bar A. Or we can also put in terms of y bar, that's also equal to rho g y bar sine theta A. So what is rho g h bar? Rho g h bar is actually pressure at the centroid. So we can conclude that the hydrostatic force is equal to pressure at centroid multiplied by area. So now we have shown that the hydrostatic force acting on the surface will be equal to pressure at the centroid multiplied by the normal area of the surface. Just now, we have determined the magnitude of the hydrostatic force. Next, we will determine the line of actions of the resultant hydrostatic force. The resultant hydrostatic force will be acting to a point which is called center of pressure, or COP. So we need to determine the line of actions of the resultant hydrostatic force. So the resultant hydrostatic force will act through center of pressure, or COP. So let's redraw again our diagram. So this is the water surface. This is the edge view of the plane. Let's say this is the normal view of the plane. The centroid of the plane is here. This is the centroid. So this is H bar. And this is Y bar. This is the Y directions. And this is the X directions. And let's say the COP is here. COP for the center of pressure. So the slanted distance between the centroid and COP is what we call YCP, and the distance of COP from the centroid in the X directions is called XCP. So the resultant force will be acting here, F, hydrostatic. So first of all, let's determine YCP. In order to determine YCP, we need to take moment about the centroid. So taking moment about centroid, what we will have is FH multiplied by YCP must be equal to the moment of individual force, rho G H bar plus Y sine theta, that's the force, multiplied by Y dA. This gives us FH YCP is equal to rho G H bar Y dA plus rho G sine theta Y squared dA. So again, by definitions, Y dA is equal to 0. So we have FH YCP is equal to rho G sine theta Y squared dA. But Y squared dA is what is called IXX, or second moment of area of A. So can write FH YCP is equal to rho G sine theta IXX, or ycp is equal to rho g sine theta ixx over fh. fh is actually equal to rho g y bar sine theta a. So rho will cancel, g will cancel, sine theta will cancel. So ycp is equal to ixx over y bar a. Okay, so we get the expression for ycp is equal to ixx over y bar a. Ixx is a function of the shape of the surface. So we have obtained ycp. So next, let's find the expression for xcp. So next, let's determine xcp here. So again, take moment about centroid, but this time the arms will be x. So we will have fh xcp must be equal to rho g h bar plus y sine theta x dA. So this gives us rho g h bar x dA plus rho g sine theta xy dA. So again, by definitions, because the origin is at centroid, that is equal to 0. And then we also know that integrations of xy dA, this is equal to ixy. So we can write fh xcp is equal to rho g sine theta ixy. And xcp is equal to rho g sine theta ixy over fh. So fh is rho g sine theta ya. So rho will cancel, g will cancel, sine theta will cancel. So again we have xcp is equal to ixy over y bar a. So now we have obtained xcp is equal to ixy over y bar a. So now we have obtained the expressions for the slanted distance of the center of pressure from the centroid, as well as the x distance of center of pressure from centroid. If the shape is symmetrical about the y-axis, xcp will be equal to 0. So we don't have to calculate xcp. In most cases, you'll have a shape which is symmetrical about the y-axis. So xcp will be equal to 0. So as a summary, say we have a liquid and then submerged plane surface slanted at an angle theta. What we need to do is first of all view the surface from the normal view, and let's say we consider a surface which is symmetrical about the y-axis. So if we determine where is the centroid, that will be our origin, the COG, and from there we can obtain our h bar, and the area of the surface is A. So the hydrostatic force will be acting through center of pressure, and whereby the slanted distance from that to that, from COG to COP is called YCP. So the force will be acting perpendicular to the surface and through center of pressure. F hydrostatic. And we have shown just now that magnitude of the hydrostatic force is equal to rho G H bar A, and YCP is equal to Ixx over Y bar A, where Y bar is the slanted distance of the centroid to the water surface. If we understand this diagram, we should be able to solve any problem related to hydrostatic force acting on plane surface. The second moment of area, Ixx, is dependent on the shape of the surface, and there are formulas available which allow you to obtain the locations of the centroid and the expression for the Ixx. So if you consider the second moment of area, let's say we have first of all a rectangle. That's the width P and the depth is D. So the centroid is, we know that is exactly in the middle there, and Ixx is equal to BD cubed over 12. So this formula is given. So let's say we have a circle. For the centroid of the circle is at the center. So Ixx for circle is pi r to the power of 4 over 4, where r is the radius. And then for ellipse, let's say we have an ellipse. The centroid is in the center, and let's say the major axis is A and the minor axis is B. So Ixx is equal to pi A cubed B over 4. And finally, if we have a semicircle, there are also formula given. Ixx is equal to still pi r to the power 4, but now it's over 8. And then the locations of the centroid is such that x equal to 0.11 r to the power of 4. So the value for Ixx and the locations of the centroids are all given, so you don't have to memorize them.